Albert Einstein, a giant of science. He gave us new ways to see gravity, time, and the universe. But even Einstein struggled with some mysteries. One of the biggest, quantum mechanics. This strange world of tiny particles baffled him. At the heart of this struggle was a concept called spooky action at a distance. Imagine two particles linked across vast distances. Change one and the other changes instantly, faster than light. This is the essence of quantum entanglement. Einstein couldn't accept it. Einstein was a revolutionary. He shattered old ideas about the universe. But quantum mechanics, that was a challenge even he seemed hesitant to embrace fully. It wasn't that he dismissed it entirely. He acknowledged its power. It could explain things classical physics couldn't. But some aspects just felt off. One of his biggest concerns was the idea of instantaneous action over vast distances. This implied a connection faster than light, and that, according to his own theory of relativity, was impossible. He believed that the universe operated on cause and effect. Events unfolded in a predictable sequence. He famously declared, "God does not play dice." In 1935, Einstein, along with Boris Podolsky and Rosen, decided to challenge quantum mechanics head-on. They devised a thought experiment. This became known as the EPR paradox. Imagine two particles born together. They share a special bond, their properties linked. We call this entanglement. Now, separate these particles. Measure one particle's property. Instantly, you know the corresponding property of the other particle. Quantum mechanics says this information transfer is instantaneous. But Einstein argued that this violated relativity. The EPR paradox highlighted a fundamental conflict. The paradox sparked debate. Einstein believed there had to be a simpler explanation. He proposed the existence of hidden variables. These were hypothetical factors, perhaps inherent to the particles themselves, that predetermined their properties from the moment of their creation. According to this view, the particles weren't communicating instantaneously. They were simply carrying with them hidden instructions, like a set of pre-agreed-upon answers to a cosmic quiz show. When we measured one particle, we weren't affecting the other. We were merely revealing the pre-existing state determined by these hidden variables. Think of it like two envelopes, each containing a different colored card, say red or blue. You open one and find a red card. You instantly know the other envelope contains the blue card. There's no spooky action, just pre-existing information. This interpretation preserved locality. But was it correct? At the core of this debate lies the concept of quantum entanglement. Imagine two particles linked in a way that defies our everyday intuition. They are not two separate entities, but rather parts of a single unified system. Their fates are intertwined, no matter how far apart they may be. Think of two coins flipped together, but with entangled particles, it's as if the coins are connected. This interconnectedness is what physicists call entanglement. This entanglement persists even when the particles are separated by vast distances. This is what Einstein found so unsettling. For decades, the debate over entanglement remained a philosophical one. Was it truly spooky action, as Einstein believed, or something else entirely? To resolve this, physicists needed a way to experimentally test these ideas. Enter John Bell and his groundbreaking theorem. In 1964, Bell proposed a way to distinguish between Einstein's hidden variable theory and the predictions of quantum mechanics. He devised a set of inequalities, now known as Bell's inequalities, which would hold true if hidden variables were at play, but would be violated if quantum mechanics was correct. Bell's theorem was a game-changer. It provided a clear, testable prediction that could differentiate between these two fundamentally different views of reality. If experiments confirmed Bell's inequalities, it would lend support to Einstein's view of a locally deterministic universe. However, if the inequalities were violated, it would mean that the strangeness of quantum mechanics, the spooky action at a distance, was indeed a fundamental aspect of the universe. The stage was set for a showdown. Bell's theorem, while groundbreaking, was just a theoretical framework. It provided a blueprint for an experiment, but conducting one proved to be a formidable challenge. It required generating and manipulating entangled particles with high precision, then measuring their properties with extreme accuracy. The implications of Bell's theorem were profound. It wasn't just about settling a scientific debate, it was about understanding the fundamental nature of reality. If Bell's inequalities were violated, it would mean that our intuitive understanding of locality was fundamentally flawed. It would imply that the universe is interconnected in ways we are only beginning to grasp. The stage was set for a new era of experimental physics. The race was on to develop experiments capable of testing Bell's inequalities. Testing the untestable, the dawn of Bell tests. Bell's theorem provided the blueprint, but actually building an experiment to test these ideas was a whole new challenge. It required technological prowess that was simply not available in the 1960s. The tools needed to manipulate and measure entangled particles with the required precision were still in their infancy. But the allure of proving or disproving Einstein's spooky action at a distance was too strong to resist. Physicists around the world took up the challenge, devising increasingly sophisticated experiments to test Bell's inequalities. These experiments, now collectively known as Bell tests, became a cornerstone of modern physics. Early attempts faced numerous hurdles. Generating and maintaining entanglement over significant distances was incredibly difficult. Despite these challenges, the pursuit continued. In the early 1980s, a team of French physicists led by Alain Aspect made a groundbreaking contribution to this field. Their experiment, considered a watershed moment in the history of Bell tests, provided some of the most compelling evidence yet against local hidden variable theories. Aspect's experiment involved entangling pairs of photons and sending them in opposite directions towards detectors placed several meters apart. The ingenious part of their setup was the use of rapidly switching polarizers. These devices could change the polarization of the photons in a seemingly random way while they were in flight. The timing of these switches was crucial. It ensured that the measurement setting chosen for one photon could not influence the measurement outcome of the other. This addressed a critical loophole in previous Bell tests, known as the locality loophole. The results of Aspect's experiment were striking. They observed correlations between the entangled photons that violated Bell's inequalities. Aspect's experiment was a turning point, but it wasn't the end of the story. Scientists are a meticulous bunch, always searching for potential flaws, alternative explanations, or hidden assumptions that might skew the results. The quest to close all potential loopholes in Bell tests became a driving force in experimental physics. Over the years, researchers have devised increasingly sophisticated experiments addressing various loopholes that could have affected previous results. These include the detection loophole, which deals with the possibility of missing some entangled particles during measurement, and the freedom of choice loophole, which ensures that the measurement settings are truly random and not influenced by any hidden factors. In 2015, a series of groundbreaking experiments claimed to have finally closed all major loopholes. These experiments, conducted by independent teams around the world, used different approaches and technologies, yet all reached the same conclusion. Bell's inequalities are violated. These modern validations represent a triumph for quantum mechanics. They demonstrate the incredible predictive power of this theory. From tiny particles to larger systems. For decades, entanglement was confined to the microscopic realm. We observed it with photons, electrons, atoms, the building blocks of the universe. But could this strange phenomenon manifest in larger, more tangible objects? Could we entangle something we could almost see with the naked eye? Recent years have seen a push to explore entanglement beyond the realm of individual particles. Scientists have successfully entangled larger and larger systems, pushing the boundaries of what was once thought possible. One particularly striking experiment involved entangling two tiny aluminum drums, each barely visible without a microscope. By carefully manipulating their vibrations, researchers were able to create a state where the drum's motions were correlated, even though they were physically separated. This experiment challenges our preconceived notions about the scale at which quantum effects can manifest. The groundbreaking work on quantum entanglement didn't go unnoticed. In 2022, the Nobel Prize in Physics was awarded to three pioneers in the field: Alain Aspect, John Clauser, and Anton Zeilinger. Their contributions spanned decades, each building upon the work of their predecessors to solidify our understanding of this enigmatic phenomenon. Aspect's groundbreaking experiments in the 1980s provided some of the earliest convincing evidence against local hidden variable theories. Clauser's work in the 1970s laid the groundwork for Aspect's experiments. Zeilinger, a master of experimental ingenuity, further advanced the field by demonstrating entanglement over increasingly large distances. The Nobel Prize recognized not only their individual contributions, but also the profound impact their collective work has had on our understanding of the universe. It highlighted the transition of entanglement from a theoretical curiosity to a powerful tool with the potential to revolutionize technology and redefine our understanding of reality. The story of entanglement is far from over. It's just beginning. Once considered spooky action at a distance, it's now a fundamental aspect of the quantum world. Quantum computing exploits these bizarre rules to perform impossible calculations. It could revolutionize medicine, materials, science, and AI. Entanglement also promises ultra-secure communication channels. As we delve deeper, more unexpected discoveries will emerge, changing our relationship with the universe. The debate between Einstein and quantum mechanics wasn't just a scientific squabble. It was a clash of worldviews, a fundamental disagreement about the nature of reality itself. Einstein, with his classical intuitions, envisioned a universe governed by order, predictability, and local interactions. Quantum mechanics, on the other hand, presented a reality that was inherently uncertain, where particles could be connected across vast distances, their fates intertwined in ways that defied common sense. The story of spooky action at a distance is a testament to the power of human curiosity and our relentless pursuit of understanding. It's a journey that has taken us from the heart of atoms to the vast expanse of the cosmos, revealing a universe far stranger and more wondrous than we could have imagined. Einstein's skepticism, though ultimately proven wrong, played a crucial role in this journey. It forced physicists to confront the most baffling aspects of quantum mechanics, to seek out ever more rigorous tests, and to develop technologies that could probe the very foundations of reality. The resolution of this debate, with overwhelming evidence supporting the reality of entanglement, has profoundly reshaped our understanding of the universe. It has shown us that the world is fundamentally interconnected, that seemingly separate objects can be linked in ways that transcend our everyday experiences. While the debate over spooky action at a distance may be settled, the mystery of entanglement endures. We have confirmed its existence, but its deeper implications remain a source of ongoing fascination and research. How can two particles be so intimately connected, even when separated by vast distances? What does this tell us about the nature of space and time? Is there a deeper level of reality, beyond our current understanding, where the seemingly separate parts of the universe are unified? The story of entanglement humbles us, showing the universe defies our intuitions. Everyday experiences mislead us in the quantum realm. Spooky action challenges our notions of locality. The universe is more interconnected than imagined. This concept is tough, even for physicists. It requires embracing the counterintuitive. Within this strangeness lies profound beauty. The tale of Einstein's skepticism and the triumph of quantum mechanics is more than just history. It's a reminder that science is about questioning and refining our understanding. Einstein's doubts pushed physicists to devise ingenious experiments. His skepticism was a catalyst for deeper understanding. The universe is full of surprises, and our journey is just beginning.